In this final part of the section, we'll begin our study of a third family of polar functions called roses. And to study roses, we'll use symmetry about the polar axis, about the pole, and about the line theta is equal to pi divided by 2. So we're going to have symmetry along these different parts of our polar coordinate system if we have the following conditions met. So condition number 1, if we have a polar function r which is equal to f of theta, and we replace our theta with a negative theta, then the graph of our function is symmetric along the polar axis. Graphically, what this is telling us is that if we know what our graph looks like between the angles 0 and pi, maybe it looks something like this. Then to find the remainder of our graph between pi and 2 pi, we just reflect this piece along our polar axis. And so we'll get a picture that looks approximately like this. The second symmetric fact that we'll be using is symmetry along the pole. So we'll have two conditions here. If we either have a polar function r which is equal to f of theta, and this is equal to f evaluated at theta plus pi, or if we can replace the r variable with a negative r, then the graph of our function is symmetric about the pole. So remember that the pole in our polar coordinate system we generally assume to be the origin in rectangular coordinates. And what this is saying is that if we know what our graph looks like in the first quadrant, then we can reflect this picture into the third quadrant as follows. And the same thing happens for the second quadrant. If we know what our picture looks like in the second quadrant, then we can go ahead and reflect our picture into the fourth quadrant. Before we move on to the next fact, let me go ahead and reiterate that if we have symmetry about the pole and we replace r with a negative r, then our function has to remain the same. So this is the extra condition that you need before you can apply symmetry about the pole. Now, jumping to our last fact about symmetry, if we have a polar function f of theta and we replace theta with a pi minus theta, then our graph is going to be symmetric about the line theta is equal to pi divided by 2. And what this means is that if we know what our graph looks like between the angles of pi divided by 2 and negative pi divided by 2, maybe it looks like this, then we can go ahead and reflect this across the line theta is equal to pi divided by 2. Now let's look at another example where we test to see if a given function is symmetric with respect to the polar axis, the pole, or the line theta is equal to pi divided by 2. In example 5, we'll be determining this information for the function r is equal to sine of 3 theta. So let's start with number 1. We want to go ahead and see if it's symmetric about the polar axis. And recall the condition for this to be true. We need f of theta to be equal to f of a negative theta. Let's replace our sine of 3 theta with a sine of 3 negative theta. Then this is equal to a sine of negative 3 theta. Now recall that sine is an odd function, and so this means that our function sine of negative 3 is equal to a negative sine of 3 theta. Again, this comes from the fact that our sine is odd. And what we obtain is that sine of theta times 3, if it was equal to a sine of 3 evaluated at negative theta, then this means that this would be equal to a negative sine of 3 theta. But clearly, sine of 3 theta is not equal to a negative sine of 3 theta, so we don't get an equality. So we have no symmetry about the polar axis. All right, let's go ahead and check the pole. So for number 2, we're going to see if our function is symmetric about the pole. And we have 2 conditions to check. The first condition that we're going to check is the following. Is our polar function f of theta equal to f of theta plus pi? So rewriting our sine of 3 theta, if this was true, this would be equal to sine of 3 times theta plus pi. Simplifying this, this is equivalent to sine of 3 theta plus 3 pi. Now we can apply our sum formula, and we'll get that this is equal to a sine of 3 theta times cosine of 3 pi plus cosine of 3 theta plus sine of 3 pi. Sine of 3 pi is equivalent to 0. Cosine of 3 pi is a negative 1. And so we're going to get that this is going to be equal to a negative sine of 3 theta. Again, clearly, a negative sine of 3 theta is not equal to a sine of 3 theta. Now let's check the second condition. Again, let me rewrite our function real fast. This is given by r is equal to sine of 3 theta. And the second condition is saying that if we replace our r with a negative r, then our function is not going to change. But solving for r and this second equation gives us that r is equal to a negative sine of 3 theta. And again, clearly, sine of 3 theta is not equal to a negative sine of 3 theta. So neither condition 1 or condition 2 is going to work, and therefore our function is not symmetric about the pole. So in our very last symmetric condition that we need to check, we're going to go ahead and see, is our function symmetric about the line theta is equal to pi divided by 2. And remember, the condition to check in this case is that our polar function f of theta should be equal to f of pi minus theta. In other words, our sine of 3 theta should be equal to a sine of 3 times pi minus theta. Simplifying this, this becomes a sine of 3 pi minus 3 theta. Go ahead and apply our, let's see, we want to apply our difference formula, and this is going to give us sine of 3 pi times cosine of 3 theta minus cosine of 3 pi times sine of 3 theta. Again, sine of 3 theta is 0. Cosine of 3 pi is a negative 1. Therefore, our equation simplifies to be a 0 minus a negative 1 times a sine of 3 theta, which is equal to sine of 3 theta. And therefore, our function is symmetric about the line theta is equal to pi divided by 2.